BFQ, budget fair queuing, I/O scheduler, helicopter view presentation, or I hope that's what you expect. I'm supposed to run this here now. So I didn't know what level to put this on, frankly, so it's a little bit of overview of the block layer and what it does, and then a comparison between the different scheduling policies. And we became involved in this through a gentleman named Paolo Valente from the University of Modena, Italy, who has been working with this BFQ patch set for a while, and it's been covered at Linux Weekly News a few times. You might have seen it. And the core of the crux, the core of the patch set is basically this. It's about user experience. So it comes from the same kind of community that have derived things like the CK kernel and other, the unnameable scheduler that Con Colevas is working with, and that kind of stuff that's very user-oriented and trying to address problems with how users experience their system. Basically, if you have media players going, if you have different audio or any kind of this, what we refer to as soft real-time tasks, user-friendly tasks. All of Android, for example, is more or less soft real-time. Then you get this thing, a very annoying phenomena that can happen at times when there is a lot of I/O, less restricted to I/O here because that's what we're talking about, a lot of I/O going on the system, and you want to do something interactive. And the system doesn't understand that my interactive stuff is actually the most important in the world right now, not your backup job, not your daemons that are serving Samba files to somebody else. It's my stuff that's most important. The system has no clue whatsoever. And that's the problem that BFQ and this kind of patches tries to address. And along the way, it also solves a few issues for the generic case. So it can look like that. You're on your media player on one of these nice Android TV things. And all of a sudden, the screen looks like that. I don't know if it's visibly here, but there are lots of MPEG artifacts all over the image. Or there's audio skipping. That's the most irritating thing in the world. Basically, or to a user, the most annoying thing is if audio is skipping. Sometimes I just prefer to turn off the entire track if that happens. Second thing is if the video is behaving like this, there are artifacts in the video. Apart from the, let's say, the humorous aspect of it sometimes, it's very, very annoying. And this happens in MPlayer or VLC or Kodi or whatever you're using when the engine is not able to fetch the data quickly enough from the file system mostly, but this could also be, of course, a streaming case, network case, then you have the same kind of artifacts. But I'm not solving the network congestion problems. That's for other people, networking group to solve. But for streaming from files from a storage media, which is of block type, 512 byte sectors, it can look like that. And we need to do something about it. And that's what Paolo's been doing with the BFQ patch set. So let's see here what we can do about it. If I can find my mouse pointer. There it is. I have a speaker notes on the second screen, that's why it's so weird. So what is a block layer? The block layer is maintained by Jens Axbo and Theon Ho and a few other people. It's a rewrite actually of the block layer, and that's been in there since the kernel 2.5 series in 2002. When we were working up to the 2.6 series, this entire rewrite of the block layer was done. And these block devices, you all know them, they look like that. They are have a block type major number and are named typically SD for the SCSI disks, including USB, mass storage, or dev MMC BLK0, etc. for the MMC cards. In the old times, there was HDA as well for IDE type devices, but that's ancient now. Mostly these are the block types we're dealing with. There are, of course, numerous others, but we don't see them so much. You might have a favorite there somewhere. So what is it doing? It serves the different processes over there with access to the block storage. So it's basically a big funnel, because there's just one device and all the processes have to share it. In the same way that the CPU scheduler allocates or allots time to different processes, this scheduler allots access to the storage media. And what's not shown here is, like, there you have the basic system calls that all the processes can issue. There are more of them, there is seek and so on, but those are the most fundamental one that came from Unix. And in between here in the funnel, there is also a file system, but it all comes down from the processes and down to the block layer, like that. Down to the drive where it's supposed to read or write a sector. So all of this open, close, write, create, etc., they will pass through a syscall interface, through the VFS, which is the virtual file system, down through a file system, and eventually into this file system turns into something we call BIO, block input-output requests, which is a list of 512-byte sector requests to be read and written to the storage medium. And the assumption is such that all storage media basically have 512-byte sectors. If it is flash, they can be bigger. And then what people do is they add something like MTD block that partitions it into 512 bytes to be able to still run the same file systems and so on. Flash is a special case. Otherwise, always 512 bytes. So in this way, the block layer mediates the block accesses down to the corresponding devices. All these requests end up in a queue of some kind here in the bottom of the funnel. And there is one block layer queue per device. So SDA has one, SD2 has one, SD3, etc., or SDB, etc. Every partition, block device has its own queue. And this takes the BIOS from the virtual file system, as I said, and then carries them down to the disk. And what the kernel I/O scheduler does is it's something that sits here in between and mediates the access to the physical blocks and prioritizes them. And as I said, it's the same principle as the CPU scheduler, just that now you're scheduling something that's much slower. It's an order of 2 magnitudes slower than the CPU. It's maybe 3, maybe 4. I don't know. It depends on how fast your CPU is and how slow your block device is. So it's a time-sharing concept. Every process thinks it's alone on the media, but it isn't. So there will be some lag and delay, but the process is not supposed to care or sense it. The only time you really feel it is when you're using something interactive and you get this kind of artifacts. So this layer needs to be smart. The queue for one of these devices, the device is per physical device, sorry, not per partition. So it's SDA, SDB, SDC, etc. They have their own queue, and they can also have their own scheduling policy, so you can do different policy on different devices. And what are policies? Policy. The block layer can register different scheduling policies for the device. They are called elevator types. It's a way of policing these requests down to the device. They can be switched at runtime if you want to. They are not compiled in or determined at boot time or anything like that. You can switch them. And when it's, then you can switch it for the entire device. Different processes can't use different policies. It's per device. And the kernel currently has 3 different scheduler policies. It's a no-op scheduler. This one was introduced not so long ago and only for testing. And it basically means requests come in from the process to read this or that sector, write this or that sector, then it's put on a list from left to right, here, 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 and then the device eats it from the end of, from the beginning of the list towards the end, and you fill in your requests in the end of the list. So it's just totally linear. There is no fairness in this. There is no prioritization. There is no coalescing or anything like that going on. It just takes it the most naive, simple policy. And you use that policy to make tests, basically, to compare it to other schedulers, and that's why it's there. So the goal of any other I/O scheduler is to be better than that, not just handle on first come, first serve basis, like when you go to a school kitchen or something, when you stand in line out here for something. That's the policy that's employed in that scheduler. Then there's a deadline scheduler, which is in block deadline sched. Jens Axbow wrote this, and this is also a quite simple scheduler. It has one big queue for the entire device. However, it is storing these requests that come in a weighted red-black tree. So it's a graph, it's not a list anymore. And the requests are then lumped into batches. So it has a certain logic to coalesce requests, for example, if they are physically contiguous on the disk, sector 1, 2, 3, 4. Okay, that's one batch. Let's take that at the same time, which is, of course, very good if it's a rotating media, because then you just write them and or read them. And the goal of that scheduler is to it tries to not allow requests to wait for too long. So the red-black tree is sorted in arrival order. So the thing that arrived furthest away in time is down to the bottom left, and that's the request you're going to pick next. It has also a few heuristics to prioritize reads over writes, because you want to feed the process, and whether the process gets its data written out is not as important, in the opinion of this scheduler. And it can perform a few front merges and back merges. So if you immediately submit a read job that is adjacent to the previous one, it will just merge it into the end of the queue. And when that request actually gets to the front of the queue and gets served, it will take the entire request at once. And that's all that there is to the deadline scheduler. It's not smarter than that. Prioritize things that were submitted long ago, coalesce some requests, and just make sure your requests don't wait for too long. It also prioritizes reads slightly over writes. But then we have the real big ones. And that's where the fun starts. Let me see if I can get up the right slide. Now we're talking. The completely fair scheduler. Oh, that's the BFQ already. Sorry. That's the CFQ. All right. Completely fair scheduler. Completely fair queue. Which is written by Jens Axbow and Andrea Arcangeli. That's his name. This is the default scheduler since 13 years in Linux. This is how we do things. So it is a weighted red-black tree, again, which inside it has queues per process. So what you're seeing here is the different processes from P1, P2, P3, P4, up to Pn, have each one of them a queue associated with them. And this combination of process and its queue, it has a weight in the system. So that weight determines how important it is compared to other processes, just like the CPU scheduler. And you will all of the time find the heaviest process in the bottom left of the tree. And then you will inspect it and see, if it needs servicing. Otherwise, you go on to the next, the most important one, and so on. And the quantum that is used to sort it and reorder the weights is the time-oriented quantum. So the time spent on each process queue is a weight divided by the sum of all weights multiplied by the entire scheduling period. So you get, if you think about it like a pie chart, you get a pie proportional to your weight. And these weights are, they are the same for all processes and kernel daemons and so on. But then there is a tool called Ionize. You can issue a prioritization between 0 and 7 from user space. And that can set the weight to bigger or smaller. And then there is a number of heuristics in the scheduler that also manipulates the weights as we go. And I can't go into all of them because, frankly, I don't understand all of them. But there is a good set of heuristics to mitigate different problems that have appeared in this scheduler. So as you see here, you have two levels. First, the requests that come in from the processes are prioritized, put in a prioritized queue, and then the queues are serviced in wait order to go down to the device. And that's how the world works right now. And they are rotated over this time quanta, so over a period of time, the process gets an allotment of the device relative to its weight, and the total time schedule, the entire pie distribution is bigger than the case when you're dealing with CPU. So this is an order 2-3 magnitudes bigger time slot than what the CPU scheduler is working on, for example. And on top of this, complicate things further. This supports C groups, control groups. So you can group 3-4 processes into a control group and say, like, this one I want to give this weight. And then that competes with the other processes or control groups in the same manner, same kind of slicing according to time. And there are heuristics, and yeah, then it needs to do some bandwidth mitigation. What that means is that when you're accessing a physical media, the read and write bandwidth down to the media varies. And that is because the most simple example is a rotating disk. There you know already by physics that it's quicker to write bytes on the outer rim of the disk than in the center. So the outer cylinder is much faster than the inner one because it's simply rotating faster. All disks spin with a fixed speed, except on old Macintoshes where they actually adjust the speed. But in all modern disks, it actually spins with a constant speed, which means that bytes are written quicker to the outer sectors than to the inner ones. And that's not the process fault. So we have to mitigate for it. And there are some heuristics related to that. So that the processes should not be punished just because the data happen to end up in the inner rims of the disk and not on the outer rims. And there are similar phenomena for solid state disks, because they have erase blocks in their flash memory and so on that you can happen to end up on, like having to erase and rewrite and so on. And that's not your fault as a process. You have to mitigate for this kind of bandwidth fluctuations phenomena. So those are the most important things about the completely fair scheduler. Then we have BFQ. And this is what Paolo and Linaro has been sponsoring. Paolo is working on it, and Linaro is sponsoring it, and I'm watching his work and saying, like, yeah, that looks good, Paolo, please do that. So I can't claim to understand everything, but I have reached this level of a little knowledge is dangerous. So what you can see here is it's very much the same image. There is weights, there is per process queues, and there's a shared queue down to the block device. But the central difference is over here, that instead of just measuring time and slicing up the time, we are measuring the bandwidth, how many bytes per second are passing through this funnel. It's the same funnel that I showed earlier in the slide. And what it tries to do is weight the bandwidth, have a bandwidth budget instead of having a time slicing, and say that let's give all processes a number of bytes per second proportionate to their weight. Now that is not the entire truth as it came up when reviewing the patch set, because this bandwidth mitigation that I was talking about is not really working when you try to do that. Then certain processes will become just very slow or very fast, just because their data happen to be stored in a slow or a fast place. So to counter that problem, the scheduler will switch back to time-based scheduling in something called virtual time. If this slice of bandwidth takes so long time that it's unreasonable to let the process go on. So it's basically somebody cannot just go up and start talking to the guy in front of the queue at the desk servicing and just press his PIN code 7 times and start asking if they have some extra premium rebate coupons and everything, and everybody else in the queue is just getting more and more impatient, right? You know this phenomenon. That's not allowed. So in order to stop that, there are some heuristics involved that switch a process back to time-based scheduling and say like, no, you're not getting any more now. No matter the bandwidth or anything, you're just eating up the time for everybody. That's actually pretty tricky. I had a hard time wrapping my head around it. So instead of saying that the process gets some time on the device, we say it gets a budget on the device. You get a number of bytes per second of the bandwidth. And then rather than just... the thing is, if we go back to how CFQ works, the completely fair queue, then that works very much like the CPU scheduler, that to switch to another task, you either have to run out of your time slice. But that's not really very common. The usual thing is that you get ready with what you're doing. You have used up the CPU as much as you need, or you have used up your disk access as much as you need. And then you just tell, well, the system obviously noticed that your read calls are out, that you have no more blocks in the queue, and then it switches to the next process. That seems very intuitive, right? If you have nothing more to do for that process, you just switch to the next. And that's not what the BFQ is doing. And that's the very clever thing about it, actually. Instead, it says, wait for a while and see if this process asks for more I/O. Why is that clever? Anybody can take a guess. Your program often reads, say if you're running a VLC or MPlayer or something, it reads an MPEG frame, starts to decode it, display it on the screen, then it reads the next frame, starts to decode it, display it on the screen, reads the next frame. And it has a buffer because you want to avoid tearing and counter slowness in network or slowness from disk I/O and such things. So you have a buffer of like 5-6 frames. But the code that reads in the frames from the disk is usually such that it reads a frame, decodes it, reads a frame, decodes it, reads a frame, decode it, read a frame, decode it. That means that immediately after I read a frame and decoded it, maybe with a GPU or something that's really quick, I'm going to issue another read request immediately. And since the CPU or GPU is a factor like 3-4 magnitudes quicker, from a I/O scheduling point of view, that really happens quickly. It's almost like it requests it immediately after the other. So if we just wait a little while, the same process will immediately request more I/O. And then this switching around to other processes, checking if is that process interested in reading and writing, that process wandering through the entire red-black tree, that takes too much time. It's better to just wait for a while, see if the process is issuing more requests, and in that case, handle them, check the budget again, wait for a little while, another request comes in, handle it, check the budget, and so on. So you avoid excess switching in the scheduler. This is one of the most clever things about the BFQ. I think it's possible to actually augment the existing completely fair scheduler to do the same thing, but it's never been done. But that is one of the things that makes it really smacky and interactive. Then it contains a number of clever heuristics that you couldn't really do with the completely fair queue either. For example, when a process is new, say when you're compiling and starting new compiler instances all the time, new shells, spawning, it boosts the weight of the newly born process. So that when this process needs to page in all its data, or read its initial states and so on, it has a boost over all other processes on the system, so it quickly gets up onto speed and can use the CPU. And then it can switch to another I/O thing. While it's compiling, for example, it's ready in its source file, it's compiling, now you can switch and do something else. So we give some boost to the processes in the beginning and do not interrupt them unnecessarily. Those are like the two most basic and user experience improving features of BFQ. So there are lots of heuristics involved there. These are not the only ones. It also manages this bandwidth mitigation. It times consumers, clients' processes out, and it punishes seeky loads, what we call seeky loads, this way. Because you can misbehave as a process. And how can you do that? Well, you can seek all over the place. Just randomly take sectors all over the disk, to the left and right. And when you do that, well, that is obviously slow if it's a physical disk and it has to move the read and write heads around. But the phenomenon is actually the same on a flash drive. And what happens then is that the bandwidth goes down, of course, because you're doing something that's really slow with the device. But you're not being punished for doing something that's really slow on a device, even though you're reading and writing all over the entire place. Now, that's not good. You should be punished for that, because it's not fair to let somebody else just run around and take up the entire disk and bring down its bandwidth so that it seems like it's not getting serviced. So you have to have bandwidth mitigation, things like that. And that's why we time out the queue and such things, to avoid that those processes just steal all the time on the device. All right, and that property is there already in the CFQ. They have bandwidth mitigation, and it's here in the BFQ as well. Okay. So we and Paolo developed the BFQ. He posted the iteration 7, I think, to the kernel mailing list, or if it's iteration 9. And it's been around for a few years. And the reaction and discussion that started then was basically about this problem, which you understand now since I've explained it this way from the beginning, that the CFQ is reasoning about things in accordance to time slicing, and the budget fair queuer is using bandwidth and time, a synthesis scheduling policy, let's say. Basically bandwidth, but also helped by time, if nothing else works. And Tae-Yoon Ho, who's one of the maintainers of the block layer, was very concerned that this way of doing things, will it really work? Will it really scale? And that's where the discussion is right now. CFQ is about slicing fairness over time, and BFQ is about slicing bandwidth over time. Or not over time, it's about slicing bandwidth and then use time as a fallback. And they are discussing back and forth whether this will work out and be fair. And one of Paolo's arguments for using the budget bandwidth approach is that in practice, when you start to measure these processes and see how much throughput they get to the device, The argument of the time slicing people is that that works just as well. I think the metaphor that Taeyun is using is a child using a swing. So if you have two children who are to use a swing, you should give them 5 minutes, 5 minutes, 5 minutes on the swing, because they both want to go on a swing. And it doesn't matter how far up and down you go or how fast or anything, you should get 5 minutes each, like 5, 5, 5. That's why CFQ. And he says it's the same thing. Whether you're on the outer rim of the disk or inner rim of the disk or whatever, doesn't matter. It should be fair. Just 5 minutes per child. And if one child is more important than the other, you give 10 minutes to one child and 5 minutes to the other. So don't do this with your kids. It's not a good, it's called dark child racing. You shouldn't do it. But with computers, it's okay to do so because they don't have feelings. However, what Paolo says is that it's not really working. When I measure the CFQ, the time-based approach, it's not working. It's starting, when you have some certain types of loads, it starts to oscillate. So you get like this bandwidth and this bandwidth and this bandwidth, and it starts to swing like this, back and forth. But when he uses the budget-based approach, he gets order of magnitude lesser fluctuations. So you get a much more steady thing compared to if you know about the people who do the deadline scheduling for the CPU scheduler, where you get a certain allotment, a guaranteed bandwidth to the CPU, a certain guaranteed time. This is the same thing about I/O, and it gives a more steady and predictable access to the device when you do that. And he has data and measurements to back it up. So that's where the discussion is right now. He has written the papers in the academic sense, but he needs to present the results to the community and convince them that it's actually so. But it's all natural sciences. It's not mumbo jumbo. And one of the examples, you could say, like, is this a server versus desktop use case problem? So that bandwidth would be better for desktops and handheld devices and so on, but servers still want to do things that way. Not necessarily. One of the examples that Paolo gives is a file sharing server, where you give out files to different users. You want to rotate this among the different users on the file share in a fair way, according to how the budget fair queuer works, not according to time slicing. So a little bit of the problem seems to be whether you are developing a system that is for machines or for humans. That's my guess. And I just entered that debate the other day, and I said, like, both parties are referring to use cases. And I know which use cases Paolo is talking about. He's talking about interactive use cases for a person sitting in front of the machine. That's the use case that he's interested in. But I get the feeling that when some of the other block maintainers are talking, they are talking about the use case for machines, for servers, for cloud computing and whatever, where machines are talking to each other about storage and so on. And that's a totally different use case. So we'll see where this discussion goes. I don't know. Yeah. I told you about that. I told you about that. Then there are some future things as well. Let's first measure what do we do? What do I do when I work with this? I mean, I spend some hours every week on this. Paolo and his team in Modena is actually not alone. He has a few PhD students there as well who worked with him. They present findings, propose solution, talk with the community, can we merge this? What I have done is to reproduce the findings and verify his solutions, and also to basically support him with anything Linux and community. So we have had lots of IRC chats and discussions, but that's not so very interesting. But I did reproduce his findings, and that's the natural sciences way of doing stuff. Like, if somebody claims they have a better solution, reproduce it, measure it, and see that you can make the same thing with the same code. And I could. It delivers. Everybody knows now. Look, BFQ delivers for these use cases that he has in his tests. It works. It makes your kernel compiles and command line things quicker and smoother because of this boosting. It does make the M player skip less when I run it. Then I have a background load. I of course could say something about what you do is run a program that Jens Axbo has written that's called FIO, which can simulate different workloads. So you start 5 to 10 different worker threads that just randomly writes and reads bytes to the disk, or sequentially reads and writes bytes to the disks. And at the same time, you run mPlayer. And then you see how many frames you skip. Simple. And it does deliver. It it identifies that this is a soft real-time multimedia workload, and it prioritizes it and makes sure that I get my bandwidth down to the device to read up the file and not get skips in my video. And then if we manage to convince the community, some people enter the discussion, we might be able to get changes upstream. And the upstream requested, last time Paolo was doing this, they requested him to replace CFQ with BFQ. That was not his idea at all. His idea was to implement it as a secondary policy, just like the no-op and deadlight scheduler. And the latest message I wrote to the mailing list on Linux block was that that Teyun says that I'm not sure that all this scheduling policy based on bandwidth is good for all use cases. But he does admit that it's good for some use cases. So my reply was, well, then maybe it should be merged as a side policy, just like the deadline and no-op scheduler. Because you initially asked us to replace CFQ with BFQ under the assumption that it would be good for all use cases and deliver in all cases. But if what you are saying is true, holds true, that it's a good policy for some use cases but not all use cases, it should still be merged, but as a selectable policy, not the default policy. So that's where we're standing right now. Then we have future concepts and other things. A funnel that looks like that with three tabs on the bottom. That's a MultiQ rewrite of the block layer. That's going on right now. The block layer authors are working with something called BKK16-107, MultiQ block layer. It involves, if I've understood correctly, two parts. One part is improving the top of the funnel up there, so that instead of having one central nexus in the system where all blocks pass through, you have queues split up per CPUs, so that different CPUs can work with coalescing or whatever the per process queues. That's one good part, and that's undoubtedly good. It makes the entire thing more scalable. But it also has this thing to it, that you can have multiple queues per device, so that this dev SDA could have 3 different tabs going out. And then this scheduling becomes much more elaborate, let's say. So I think that what's inside of the MultiQ scheduler right now is one of the most naive ones. It's basically no-op. Just toss it down to the device as quickly as possible, because it's still going to be faster than trying to put it through some scheduler. But that's another universe that's opening up. And of course, that never happens. Well, it could happen if you have several read and write heads on a physical device, but you don't usually access them with software. So in that case, you make it into a hardware problem. But on a flash device, you can issue several commands in parallel to read and write sectors. And that's when it starts to look like that. And then you need to rethink the whole thing. It's been engineered and built up under the assumption that there's one pipe down to the device. So I think that currently they just take out the scheduler, force bytes down all the 3 pipes, and still get a better performance. But there should be some scheduling involved, and they're working on that right now. But what we know for all the mobile and, let's say, handheld devices, today we're using MMC SD cards. And those are, by definition, not MultiQ. There's nothing in that protocol that is multi-queuing. It has command queuing, which is a kind of, it's similar to software pipelining, that you execute things in parallel in a pipeline. But if you get a bubble in the pipeline or a stall or an error in the pipeline, you have to reverse out of all the work. And that's what happens with command queuing. Did anybody understand any of that? I mean, it's sort of hand-wavy. But It's not really that you're writing things in parallel and that the different requests can complete independently. Instead, you can queue up a batch of work and send it down to the MMC or SD card. But there's no way to do things in parallel because it's a request-respond protocol, and nobody has really made a host that can send several commands. And I don't think the protocol allows it either. It says, like, send one request down to the card, get the response back. So no multi-queuing on this side. Up on that side, among the processes, you can have multi-queuing. Though it will probably not help because the end of the funnel is going to be the bottleneck. Let's see if we have something more on these slides. Yeah, we also have right-induced latencies. This was observed by Paolo in his work. That if you have small bursts of write in certain places of the disk, it sort of clogs up the entire system. And what are these bursts? They are demand paging things, and they are journal writes for things like Btrfs and ext4 that take precedence over all other writes to the media because it's done by the file system, and the file system daemon takes up all the time and the bandwidth, and it writes all over the place, small spurious writes everywhere. That's really disturbing the scheduling policy. So when we get a lot of types of that type, and we have to provide some very special synthetic use cases to get to them, then things start to go really bad. So one example with small writes is updating an Android app. Then you're writing some class files here and there all over the place, or you're writing like all over the file system. You get it fragmented, and updating a few packages, RPMs or something in a distribution, or Debian packages or whatever you're using, same thing. That slows the system down, and you probably noticed it if you've done these updates and tried to do something else at the same time. It gets really slow and shaky at times. Why is it doing that? That's not necessary. That's not the law of nature. It's because of this thing. So that's the next step. Once Paolo gets his budget fair queuer in, the idea is to go on and work with this kind of latencies. Right-induced latencies when you have small spurious writes. All right. That's all. Any questions? Daniel. Yeah.
So you mentioned that BFQ does read anticipation. Anticipating the next read from a read-heavy job, and that it wasn't contradicted by CFQ. So CFQ could do it but doesn't. So when you get better benchmark results, how do you figure out which bit contributes? How do you know the bandwidth is important compared to the actual the read anticipation?
I think he hasn't tested to implement the same heuristic on CFQ because he first determined on the paradigm of the budgets. I think academics think about what is the resource we want to distribute, and they come to the conclusion we need to switch paradigm to distribute bandwidth and not time. And then they come to this dual solution where they also have a time out of it. But it's not really anticipating that they well, it's anticipating in a sense. Maybe my English is not good enough. It's just waiting and seeing if something comes in. Yeah, okay. Yeah. Okay, yeah, it's waiting and seeing if something turns up, and it's anticipating that, yeah, probably they will ask another request. Yeah. I think he hasn't tried. It would be interesting to do an anticipatory patch to the CFQ scheduler and see what happens. Yeah, I don't know if it's possible to make a patch like that. I'm just guessing it, basically. But I think Tejun said on the mailing list as well that he thinks that the same heuristics can be done on the CFQ. First, he sort of dismissed the entire concept of bandwidth distribution over time distribution. And then Paolo answered, and then he took a step back and said, okay, you do deliver on some use cases. So then then it was like, but I'm not really sure that this is the good way. So now the discussion is a little bit pending there. Any other questions? Everybody's 100% certain how BFQ works. You want the mic, or you want to shout? Yeah, okay.
Okay, so actually 2 questions. First one is for BFQ, how do you decide when to fall back to using CFQ? And second question, if I want to try these patches, they weren't merged for now, right? So if I want to try BFQ, how it's implemented? It's instead of CFQ, I will be using BFQ if I merge these patches, right? Okay, so.
The first question is how it decides to switch back to time-based lighting. It's a timeout, basically. I don't know the exact specifics, but the way that it is described is that if you're using your I/O slice very slowly compared to a virtual timeline, then after a while there will be a timeout, and if this happens a few times, it switches back that process to only do time slicing. So it will only get time on the device. It will not get bandwidth anymore. But I don't know the exact limits. I would have to read the code. Then where to get the patches and test them? There I have actually a really good answer, because I maintain that tree together with Paolo. Let's bring up a web browser. So it's at GitHub /linux-w/linux-bfq. That's the kernel tree. And you can check out the different branches. You see there are 13 branches here. There. Look at the latest updated one, and you will find some different kernel baselines. I'm using it on that laptop for this presentation. It's running BFQ. I have recompiled my Fedora kernel for it, and with a vanilla upstream 4.5 RC3, and it's just working. I've never experienced any crashes or dubious behavior or corruptions or anything like that with the BFQ. It just works. So you really have to stress it if you want to make it break. And the discussion is not really about the patches being unstable or anything like so. It's only about whether it performs compared to CFQ or not. David.
So how have you tested for data corruption and what have you? Have you done any analysis just to see if the queuing stuff has messed up the data that gets written to the disk?
So this is my development laptop, and it's basically just filled with a lot of Git trees. And you can check the integrity of your Gits, and I do that repeatedly. So I will notice immediately if something corrupts there. So the entire hard drive is full of Git. And that's where I'm reading and writing all the time when I'm developing. So I'm just actively developing on that machine and see if something screws up. And my Git trees have not become inconsistent. That's the test I've done. Very amateurish and ad hoc, but at least something. But Paolo has done more extensive tests over time and so on, and checksumming his file systems and doing the same image with operations before and after this scheduler. So it's working, I think. There have been bugs and lockups, but they have been more of the type related to group scheduling. So if you're using group scheduling, it might be a bit shaky. And Android is using that actually, I think. It's nowadays it's putting some of the processes into a root group and so on. Something dangerous might happen if you're doing it on Android. It's been tested. We tested it with Linaro on Android, and it delivers on Android. Makes the test that was done by Mariusz, is that the name? Let me see here, so I'm crediting the right people. Milos Wasilewski. Are you here, Milos? No. Milos, he tested to start a few different DD commands, reading and writing sequentially, not random DD, so it's just sequentially, to the internal MMC card, and then start a calculator app in Android. And it resulted in a 50% improvement in startup of the calculator application from 130 seconds without these patches to 44 seconds. No, to 87, 130 to 87, so you save 44 seconds. So, and that's 44 seconds of somebody's life, and if you multiply that with entire Android base and everybody has this problem, it becomes quite a lot of years. But the typical use case you see is that you're updating an application. You know this little arrow on Android on the top when it's updating an application, and you try to start something at the same time. It can get really slow. And that's what BFQ helps improving the user experience in that case. And that's why I think that, I don't know about why with CyanogenMod, but CyanogenMod is including these patches. And this should be the rational reason, but when I look at CyanogenMod, it seems that they are including patches just because they are fun and for not very rational or tested reasons. Just because, oh, a smart guy, he made a patch, let's include it. So I would take their usage of stuff with a grain of salt. Arch Linux are deploying it, and they are more serious in my opinion. So they also use BFQ for their NAS distributions, and it seems to be delivering for them. And I'm using it myself, so I'm partial. Also ask the proper block maintainers what they think. They will say I'm stupid. All right, are we done? Thanks.